Hello and welcome to Algebra 2 tutorial. In this video we're going to take a look at mathematical modeling, and in particular linear modeling is what we're going to start with here. So that kind of has three different phases. The first is gathering data, and then once we have our data from our experiment, we're going to be analyzing that data. In short, that's making an equation to model it. And then using that equation to predict is our third phase here. So first we're going to be gathering our data from a hypothetical experiment. So let's take a look at that. So our experiment here is going to be rolling a ball down a ramp, and then that ball will continue going a certain distance down this way. So our ball will go down the ramp, it'll gain some speed, and then it'll roll along, say, the hallway, and we would measure how far along the ball would go. So the first thing you want to do when you're doing this experiment, before you even take the numbers, is identify your independent variable and your dependent variable. What are those going to be? So that can sometimes be a little difficult. So in this case, our independent variable, that's what you control, oftentimes. So what are we controlling? The one thing we are going to be controlling is the height of the ramp. So we're going to set the ramp at, say, a height of 1 foot, and then see how far it goes, a height of 2 feet, and then see how far the ball rolls, etc., etc. And the dependent variable is often what you are measuring. In this case, we're going to be measuring the distance the ball rolls. Oftentimes, to make sure you have those correct, you can put them in a sentence. Blank depends on blank. And when you fill that sentence in, it should make sense. And just try it out. Does the height of the ramp depend on the distance the ball travels? Hopefully that doesn't make any sense. The distance the ball travels depends on the height of the ramp. I'm hoping that makes sense, and that kind of gives you an idea of what is dependent on what. So let's say we do this experiment. We raise the ramp up 1 foot, and let's say the ball goes 25 feet. And then we raise the ramp up 2 feet. We let the ball go, and it travels 40 feet. For 3 feet, it then goes 70. And then 4 feet, 82. And for 5 feet, a 5-foot ramp, we're going to go 105 feet. Now, I did just sort of make those up, but they will give us some numbers for a hypothetical experiment here. All right, next, it is good to identify your domain and range. Your domain is, of course, your x-axis, all your x values. And so right now we're going from 1 to 5, but theoretically you could do any size ramp you want, but that would have to be positive values. So these are positive values. And if you want to write that in math syntax, x would have to be greater than, or I suppose you could have a ramp that is equal to 0 feet. And your range are your y values. So again, take a look at these y values. They also all look positive. So your y values will also be greater than, and I suppose if your ramp is 0 feet, the ball would technically probably go 0 feet as well as the ball rolls. So 0 is probably also an option. All right, so there we have sort of the setup and the data for our experiment. And once you have the data, and once you have all the experiment done, you can move on to analyzing your results. And so that's what we're going to be doing next. Now that we've gathered our data, we're going to analyze the data. And the way we're going to analyze is by drawing a graph and by making an equation. So real quick, I'm going to put our data back here so we can see it We have our x values and our y values. When it was at 1 foot, we were at 25, 2 feet, 40, 3 feet was 70, 4 was 82, and 5 was 105. So my graph isn't completely perfect here, but it will work pretty well. So let's plot these points. At 1, we are at 25, so right about here. And then at 2, we are at 40. 3, we are at 70. So I'm going to go off my graph a little bit, but I suppose it'll be right about here. And 482, which I suppose will be even higher. We'll put it up here somewhere. And we sort of get the picture of what this is doing. We have a fairly straight line coming up this way. Something like that. And so what we're going to do is, what would the equation of that line be? Technically, it's called a line of best fit. Now, there's many ways to do a line of best fit. We're going to take a very easy way that's going to practice an old Algebra 1 skill. We're just going to take the first point we got and the last point we had, and we're going to write an equation based off of those 2 points that looks like y equals mx plus b. Just a linear line between those 2 points. So first we need the slope, and then we're going to need the y-intercept. So m is our slope, so we simply take these two and subtract them. If you remember, that's y2 minus y1 over x2 minus x1. So we subtract the y's and we subtract the x's. So on top, we get 105 minus 25. And on the bottom, we get 5 minus 1. So we subtract them. On the bottom, we get 4. And on the top, we get 80. And 80 divided by 4 is 20. So we have our slope is 20. That is going to come up right here. So we basically have part of our equation already done. We have y is equal to 20x, but we don't know the b, so we need the y-intercept. So to do that, we're going to take an x value, and we're going to take a y value, and plug them in. And so we'll do that to find b. So y is going to be 25. And 20, our x value is going to be the 1 plus b. And as you can see, we only have one variable. We should be able to solve this. 20 times 1 is just 20. And so then we're going to subtract that from both sides. And 5 is equal to b. So now we have m and we have b. We now have the equation of this line. This line is y equals 20x plus 5. So that is the equation that now models how far this ball will roll down if we raise the ramp to a certain height. Now that's a little weird because we have a context. We have ramp height and we have distance, but we also have y's and x's. And so what you'll sometimes see here is we'll change this y and x format and put it into function notation with letters that actually make sense to our problem. So y is the distance our ball travels. So we might use d for distance. And x is the height of the ramp. So we might call that an h for the height of the ramp. And then to put it in function notation, you'd say d at h is equal to 20h plus 5. So there is our model in function notation. Hopefully you can see how that is basically the same as our equation with y and x. But oftentimes the letters here, the D and the H, make more sense because they connect with the context of the problem, distance and height. All right, so we've done quite a bit of analysis there. So now that we've gathered data and we've analyzed it, it's time to use our analysis to do some predictions. So here are two questions you can use to predict using our model now. So the first one, how far would a ball roll if you raised the ramp 10 feet? Now we didn't actually do that hypothetically, but what if we did? So remember our model that we have, the distance at a height is equal to 20 h plus 5. And this is what we're given right here. This is raising the ramp, so that is a height. That is going to go in for h. So d at our height, which is 10, so we're going to plug in 10 for h, is equal to 20 times 10 plus 5. So d at 10 is equal to, let's see, 20 times 10 is 200, plus 5 is 205. And when you use function notation, you get the whole answer in context together. So the distance the ball will roll when you raise the ramp 10 feet will be 205 feet. So here you see the input and the output in one statement, which is always very convenient. All right, now how high would you need to raise the ramp if you wanted the ball to roll 150 feet? So here we have a different value. This is not the input, this is the output. It's not a height, it is a distance. So that is going to go in for d. So I'm going to write my equation again. D at h is equal to 20h plus 5. This time I'm not replacing the h, I'm replacing this whole output d of h. That whole thing is going to be 150 is equal to 20h plus 5. And again, we only have one variable, so we just have to solve this. Subtract 5 from both sides, minus 5, minus 5. So we get 145 is equal to 20h. Divide by both sides by 20. Divide by 20. That goes away. You are left with h is equal to 145 divided by 20. So that is 7.25 feet. So that is how high our ramp would need to be in order to have a 150-foot distance for our ball to be rolling. All right, so that's our predictions. Let's clear that out. Let's take a look at everything we've done now. We had an experiment where we gathered data, we analyzed that data and made an equation and a graph, and then we used that to predict new situations that we hadn't actually done yet. So I'd like you to try and practice a problem of your own here. So you can go ahead and pause the video. You should be able to do all of those parts, A, B, C, and D now. They're just like what we did. Good luck.